Okay, folks, sorry about that. I had to restart the video. So, what we're going to talk about now are conjugate additions. Now, we talked about this in the last video. I'm just going to summarize it very quickly. Conjugate additions happen when you've got an alpha-beta unsaturated carbonyl and a nucleophile. The nucleophile, which most often is a double enolate. And what that means is something that looks like this, where the negative charge can resonate through the two carbonyls equally, a double enolate. The nucleophilic addition would look like this, where the nucleophile would attack the beta carbon, the pi bonds break, form a new bond between the carbonyl carbon and the other carbon of what used to be the carbon-carbon pi bond, break open the carbonyl oxygen pi bond, and what we have is this. And now, with just a trace of acid and tautomerization, what you're looking at is this. In the last video, we discussed what enolates would do this. As I said, double enolates that can exist between a whole bunch of things. So what substrates will this work? What substrates are we talking? Well, alpha-beta unsaturated aldehydes, ketones, esters, amides, and finally these two weird ones. An alpha-beta unsaturated nitrile or an alpha-beta unsaturated nitrate. All of these can be substrates for a conjugate or Michael type addition. Now, what I want to do is I'm going to give you a problem that I want you to work on. All right? Here's the problem. I want you to react this alpha-beta unsaturated carbonyl, this diketone, with potassium hydroxide followed by this alpha-beta unsaturated carbonyl followed by a little bit of acid. So hit pause, work on this for a couple minutes, and we'll talk about it when you get back. Oh, hey, you're back. I missed you. So here's how this would work mechanistically. The key in understanding this, how this works, is, do you see the 1, 2, 3? The first thing we do is we react the diketone with the base. The second thing is we follow it up by whatever formed from that reaction, the diketone and the base, attacking the pi bond of that alpha-beta unsaturated carbonyl. Finally, the acid group. So here's what happens first. The base will deprotonate the diketone, and you get here. Now, I've got this weird, almost fetish for enolates drawn this way. Your book shows it a lot like this, which is exactly the same way as I have it written. So if you want to go with that, I cannot fuss at you about it because it's not wrong. I just prefer this enolate form, maybe because that's how I was taught. And now we formed that dienolate, which means we now introduce it to your friend and mine, the alpha beta unsaturated carbonyl. And now we have this. Oh, wait, messed that up, sorry. This is where I fell afoul last time I did this video, too. There we go. Now we're here. And we add that little bit of acid for the sole purpose of making this, which is your major organic product. This is your major organic product. All right, let's do something a little different. We're going to do, I want you to work on this. Sorry, folks, that shut off and I'm not exactly sure when. So let's rewind just a little bit and see. This was your major organic product that we made. Hopefully you all saw this and that didn't get lost in the translation. Now what I would like you to do is take a look at these three alpha-beta unsaturated molecules. The first one is a ketone, the second one is a nitrile, and the third one is an ester. What I would like you to do is react that with the diethyl lithium cuprate. This is a Gilman reagent. And the other thing you got to remember is this is kept at minus 78 degrees C. If you take a Gilman reagent and you try to react it at 0 or above, it's going to act just like every other organolithium. Doing it this way, however, through the Gilman, you'll get a different set of products. So go ahead, think this through, come back, and we'll talk about it. Hey, welcome back. The thing about the Gilman reagent that you need to remember is this. It's going to do a conjugate addition. So, without worrying about the mechanism here, because these are pretty complicated mechanisms, what I'd like you to see is this. The product for the first one would look like this. Actually, I found a better way to write that. It would look like this. The second one would look like this. And finally, this ester, which I don't know why I just rewrote that because I didn't need to. This ester would look like this. That's how the Gilman reagents work. So, all that being said, let's work a few more problems. I'll probably do a couple more on this page. I got one new reaction to show you, and then we're going to do one more short video after this to talk to you about probably my favorite reaction in this whole unit. All right, so here's what I want you to work on. Let me change that. I'll use white. I want you to react this alpha-beta unsaturated carbonyl with I'll draw it better than that, I promise. that diester with methoxide, followed by acid and water, followed by high heat. All right? So think about that. Come back in just a minute. I'll show it to you. All right. So the product would look like this. Now, for those of you looking at me going, how the hell did you do that? Let's see. I'm going to skip one little bit of a step and go ahead and use the enolate of this diester. Hopefully you can see where that came from. It's going to nucleophilically attack the ketone. Break that open. Send that pi bond up there. Which puts you here. Now, acid and water will serve two purposes here. The acid and water will, one, turn your enolate down there into a ketone. And second, oh, bollocks. I've balled this all up, haven't I? All right, folks, here's what we're going to do. We're going to do this one in the next video where I won't screw it up. So, see you then.